In this video, we're going to be looking at the concept of two-dimensional uniform motion. This is when objects move with a constant velocity along both the x and the y axis at the same time. What are we going to do? We're going to review the concept of uniform motion and resultant motion. We're going to also apply that concept of uniform motion to objects that move along both the x and y axis at the same time. We're also going to develop and use a strategy that's going to break large two-dimensional motion systems into smaller, easier to work with one-dimensional motion systems. Why are we doing this? Because most objects do not move along only one axis, but often move among two or three axes. Also, breaking systems that use two or more axes into smaller, easier to work with systems is a key skill that is used throughout physics as well as engineering. So here we have a situation where we have a person who is standing on the shore. They are a stationary observer, and they are seeing a boat travel across the water. The water is still, so there is no current, so it's kind of like a lake. And the boat on its own travels with a speed of 5 meters per second. If it's going to the right and we have to state the direction, we can even write this as a vector because it is moving to the right, which has a direction. The boat is going to end up at a house that is 300 meters away from the person. And the question is, how much time does it take for the boat to reach the house? This type of question is pretty basic and we've worked with before. I can easily use the concept of average velocity, which by definition is displacement over time. The boat has a displacement of positive 300 meters because it's to the right of my screen. The velocity is positive 5 meters per second because it's also to the right of the screen. So 5 meters per second equals 300 meters, positive 300 meters over the time, because average velocity again is displacement over time, and I can find the time is easily 60 seconds. But let's say I have a situation where there is the boat traveling at 5 meters per second, just like before, but instead of a lake, this is a river, and the river is also flowing at 5 meters per second to the right. How much time does it now take for the boat to reach the house? Well, the truth is, this stationary observer is not going to see the boat move at 5 meters per second. And the stationary observer is what is the ground as well. So whatever the person sees, the ground sees. So the person's going to see the boat move faster than 5 because the water is aiding the boat. So the ground would see the boat travel faster than 5 meters per second, which means as far as this 300 meters is concerned, the boat isn't traveling at 5, but something faster. So for this situation, what we can say is that the boat's resultant displacement is going to be positive 300 meters. We're going to say resultant displacement because the boat on its own didn't travel 300 meters. The boat's motion plus the water's motion caused the boat to travel 300 meters in whatever time that it took. So we can now say that the average resultant velocity is equal to the resultant displacement over the time. So I need to add up the velocities of both the boat and the water, because this is motion in a stream, to find the resultant velocity. That velocity will equal 300 meters positive over time. And so by just simply doing vector addition tip to tail, we can see that the resultant velocity is 10 meters per second to the right. So at a rate of 10 meters per second to the right, the boat will have a total displacement of 300 meters to the right. So this now happens in a time of 30 seconds instead of the 60 before. This means in the time that it took to get to the house, the boat only traveled 150 meters on its own. But the water carried the boat an additional 150 meters, which is why it traveled 300 meters. So that's what we're really looking at here. We're going to just simply be adding up our vectors, velocity vectors, to find out what the combined effect is. And as always, the resultant velocity will give us a resultant displacement. And always, resultant velocity is always the velocity of the object plus the velocity of the stream or streams that are affecting that object's motion. all as seen by a stationary observer, such as the ground or the person who is standing still on the ground. So in the first case where we have like the lake, my resultant velocity is just the boat because the water is at rest. There is no velocity. So 5 meters per second positive plus 0 is the 5 meters per second. So a lot of times we drop the word resultant and we'll just say boat because there's only one object there. But it's important to note that that velocity is still a resultant. I am adding a 0 to the 5. In the river question, where we have the water flowing at 5 meters per second, it's much easier to see the resultant is just going to be the two velocities of the boat and the water is being added up together to make the combined 10 meters per second positive. Let's now look at a situation where I have the boat, but instead of going with the river or along the river, it's going to go across the river from one side to the other. The distance the boat can travel to get to the other side is 200 meters. It's going to move at 5 meters per second. The water is still, and I want to find the time it takes to get across the other side. Well, this is very similar to the very first question where I was going across the x-axis. This is solved exactly the same way. The only minor differences that you can think about is that the displacement, since I'm going down, is negative, and my velocity, since it's also going along the negative y-axis, is negative. So negative 5 meters per second equals negative 200 meters over the time, which gives me a positive time of 40 seconds. Every time we solve for time, we should always come up with a positive answer. If your answer does not come out to be positive, first check to make sure that all of your signs are correct for your velocity and displacements. If they are correct and your time is negative, then you're looking at a situation that is impossible or you have some other error that is there. But now let's turn around and say the boat wants to go across the river, but the water is moving at 5 meters per second to the right. The person who's piloting the boat does not compensate for the current, so they're going to just point that boat straight down and get pushed sideways and not even try to correct for that. And the question now is, how far along the river did the boat get pushed? So anytime you're going parallel to the surface or parallel to the shore, we call this along. And when I go from one side to the other, that's always across. So the question is, how far along the river do I get pushed? Well, we have multiple things happening here. I have some motion that's going to go across the river, some motion that's trying to go along the river. Both are happening at the same time. Both are equally important. Both are equally valid. It's like when two people are trying to argue and you're trying to listen to them, you just can't make sense of what's going on because too many things are happening at one time. That's why a lot of times when two people are trying to get their point across to a third party, the person who's trying to listen to both people tell one of them to be quiet for just a little bit and let one person speak, and then they'll hear the other person. Each gets their turn, but you just can't speak at the same time because we can only process one thing at a time. So the first thing we're going to do here is we're going to break everything up into vectors. So I have a displacement of negative 200 meters for the y-axis, and I do not know the displacement for the x-axis. I have a velocity of negative 5 meters per second for the y-axis and positive 5 meters per second for the x-axis. And I can only work with one of these axes at a time. And since I really can't find anything with just velocity, because I need time for displacement, I'm going to look at my y-axis first. And if I was to pretend the water was still, I would see that the boat travels negative 200 meters at negative 5 meters per second, so it takes 40 seconds to go across the river. Now, if the river is moving sideways, that doesn't affect the downward motion. X-axis and y-axis are independent. So we will often break things up into components of both x and y's because we can focus on one aspect and then take what we need from that aspect to apply to the other. In this case, I could not solve for this displacement because I do not know what the time is. But by looking at just the y motion, I know the time is 40 seconds. So now I can take that 40 seconds and apply it to the X motion because I only had 40 seconds to move along the river because it took me 40 seconds to get across. After 40 seconds, I'm hitting the shore on the other side. Thus, I stopped moving. So I can now turn around and say 5 meters per second positive times 40 seconds is positive 200 meters. And I'm just taking my velocity definition, displacement over time, and I'm applying it for the x-axis. If I wanted to find out what was the resultant motion of the boat, how far did the boat truly travel, and in what direction? So in short, looking at my observer, what did they observe? Because they didn't see the boat go like an Etch-a-Sketch line going down and then sideways. What they saw was the boat going diagonally across the river, from not straight across, but diagonally along this resultant line. So we can easily find this resultant by taking my x displacement and my y displacement and adding them up like vectors because they are simply vectors. I can add them up with a ruler and protractor drawn out tip to scale, tip to tail by scale, and see what my resultant is. I could also use Pythagorean theorem and use trigonometry such as sine, cosine, or tangent to find the angle. Either approach is up to you. It doesn't matter what approach you use. If I wanted to find the overall resultant velocity of the boat, how fast was it really moving because of the boat's motion combined with the water's motion, I can use the definition of velocity and say it's displacement over time. My resultant velocity is the resultant displacement over time. So since my resultant displacement was 282.84 meters at 45 degrees to the right of the negative y-axis, I can divide that by 40, where 282.84 meters divided by 40 seconds is 7.07 meters per second. The direction of the resultant velocity is always the exact same direction as the displacement vector, the displacement resultant vector, because the velocity resultant made the displacement resultant. So they will always be in the same direction. But if I didn't want to find the displacement, I just wanted to find the resultant velocity, I could also just look at the velocity vectors involved on the boat. I have the boat's velocity and the water's velocity and add them up like vectors. And that's because my resultant velocity is just the sum of my object velocity plus my stream velocities. But they are vectors, so I add them up vectorially. I'm just not adding numbers up. I have to do them tip to tail. This is kind of misleading when we have the boats that are in water that go in the same direction, because that looks like I'm just adding up my numbers, but I'm not. I'm adding them up tip to tail. It just so happens when vectors go in the same direction, vector addition results come out to be the same as just scalar addition results. But that's the only case. So in this case, since my velocity of the boat and water form a right triangle, I could draw these out to scale using a ruler and protractor, doing it tip to tail, of course, and I could come up with my resultant. Or again, I could use Pythagorean theorem and use my sine, cosine, or tangent to find what the angle is. There is no more correct approach for us. They are equally valid. So you just use the method that is you're most comfortable with. And if later on in the course you decide the other method is more suitable to your likings, then you switch. That's totally okay. Remember, when working with vectors, we'll often see a right triangle. It won't always be the case, but we'll often see a right triangle. And when working with the right triangle, we can always use Pythagorean theorem, which is that the hypotenuse squared is equal to each side squared added up, and that the tangent of the angle is the side opposite of the angle divided by the side that is adjacent to the angle, the adjacent side not being the hypotenuse. These are not base these are base equations, so you do not need to have them memorized. They're always given to you, and you can use them if you choose to. A major problem that people run into is the assumption that my resultant is always the hypotenuse. We will see situations where the resultant may not be the hypotenuse. It might actually be a shorter side of the triangle. This is why it's very important to always draw out what your vectors look like and arrange them tip to tail. Even if you're not going to use a two-scale diagram, you need to have it drawn out to make sure that when you're solving for your resultant, you're solving for the right leg of the triangle. Not only that, but sometimes people will get their angle wrong when dealing with their tangents because they have inverted the two sides. And that's because, again, they didn't draw out their triangle. And so sometimes they will have the opposite where the adjacent should be and vice versa. For example, if I had this triangle and I was looking for the theta up here in the top corner, tangent is b over a. But let's say I was looking for this angle over here. Then the tangent is a over b. It's easy for me to make these mistakes if I do not draw out my vectors. So always make sure you draw them out. Always has a quick reference. No one has ever drawn out a vector triangle and regretted doing it. Keep in mind that mathematical equations and physics definitions run the same way. They represent the same thing differently. Now, when in doubt, definitions always win. Always refer to that first. Mathematical equations might have a restriction. This works if this condition is met. Definitions work 100% of the time. If it didn't, it wouldn't be a definition. Our mathematical equation for a resultant is always the summation of their vectors. So resultant velocity is the summation of all the individual velocities. But by definition, the resultant velocity must be displacement resultant over time. So I can easily just combine my mathematical equation and my physics definition and simply say that the sum of my vectors added up, my sum of my velocity vectors added up, is equal to my resultant displacement over time. This is important because this now provides two similar triangles, the velocity triangle and the displacement triangle. And since the angle of the velocities must be the same angle as their displacements, these two triangles are similar. Similar triangles are always proportional to one another. In fact, here I have my resultant velocity triangle through the Pythagorean theorem. And if I was to write out my resultant velocity as the definition, displacement over time, I get the following expression down here. But let's say I was to multiply this equation all by time squared. So if we go ahead and multiply all sides of this equation by time squared, we would see that all the times cancel out. And I am left with displacement resultant squared equals the displacement of the object squared plus the displacement of the stream squared. I have the Pythagorean theorem for this triangle. So I can easily work a proportionality between these two triangles. So here we have our classic situation that we've just seen where the boat is trying to go across the river. It's being pushed sideways. The pilot of the boat did not compensate for the current, so they just got pushed 200 meters downstream. And we have a whole lot of information here. And there should be some fairly easy methodology that we could use to solve for my ending location and my displacements, and there really is. And it all comes down to straightforward organization and separation of the material or the information. So here's that very same situation as we would have initially set for a problem if we were trying to solve for my displacement for the x-axis as well as my resultant. And we need to come up with some methodology to solve this out. Now, if you remember, we looked at the x-axis and the y-axis separately. So that's what we're going to really do here. One of the first things we do, though, is we need to have a reference that we can use to measure all of our displacements from. To solve a problem like this, we're going to use a tool that is known as a T-chart. The T-chart will allow us to isolate information for both the x-axis and the y-axis and allow us to focus our attention on one of these two axes to solve for the needed information to answer the question that we're being asked. The way the T-chart works is through a very simple four-step process, and you're going to see that many of our processes or problem strategies will take 4 steps, and they often have a very similar format. The first step is always going to be to draw a system of the situation and set up an origin. This way we know what we're looking at, and then we can identify our values as positives or negatives, x and y's, and we're talking about specifically positions and velocities. The next thing we're going to do is we're going to take the definition of average velocity and manipulate that into an equation for position final. So since average velocity is the displacement, which is the change in position over time, we can solve for position final by multiplying time to the velocity and then adding position initial to the other side. So position final equals my initial position plus my average velocity times the time. I'm going to have this for both the x motion and the y motion. Then I'm going to use the time I find to answer the question that I'm looking for, because that's the whole problem here. And when I looked at this problem, I can't solve for anything because I don't know the time. So that's going to be my trick. We often use the T-chart to find the time to then solve for whatever else we're being asked to solve for. So we have a situation here where I have a boat that's going to cross a river, and I want to know how far down the stream does it travel, and what is the boat's displacement and resultant velocity. And if you notice, I said the boat's displacement, since we didn't say x or y, that's already being implied that's the resultant displacement, because the boat does start here and end over here. So this is the boat's displacement. So the first trick I'm going to do here is set up an origin. So I have my origin at the boat starting location. My velocities are negative for the y-axis, positive for the x. I can also say that my x position is unknown and my y position is negative because it is below my xy axis, my origin, so it should be a negative value. I can even think of it this way. As of right now, looking at just my coordinate system, this is in quadrant 4. So we have quadrants 1, 2, 3, and 4. And when I'm in quadrant 4, I should have a positive x and a negative y. And that's exactly what we see here. You don't actually have to identify your quadrants if you don't want to. It's just a little thing I wanted to point out to help justify why I have my y as a negative value. I can now use my position equation and plug in the values for both the x and the y axes. I always plug them in both for the x and y at the same time because I may not see automatically what side of the chart I'm going to use first. So when I look at this side here, I know I can't solve for position because I don't know my time. So I just look at my y side and I can easily solve for my time since I know my initial position, my final position, and the Please notice that the 3 meters per second for the x-axis is not on this side of the equation, so I don't have to think about it. This also gives me the mental aid of not being distracted by things that are irrelevant to what I'm dealing with. When I'm looking at the y motion, the x does not matter at all, so I can pretend as if the water was stationary. Once I have the time, I can then focus my attention on the X, and I don't even have to worry about the Y side anymore because I have everything that I need from that side. So I can easily find the time, which is 4,100 seconds, and I can now take this and plug it right into my time for this side. Now, as of this time, I know what the time is, so I don't care about the Y motion at all. I just needed the time, and that is it. So plugging that time in, I can see that my position for the X-axis is positive 12,300 meters. So this unknown has just become positive 12,300 meters. So now I have a final position. To find my displacement, I can now very easily just use my right triangle and go Pythagorean theorem and arctangent to find out what my displacement is. If I'm looking for my resultant velocity, I can use my velocity triangle to go ahead and solve for my resultant velocity. So here I have my velocities drawn out, tip to tail, and I'm going to just simply use Pythagorean theorem. And again, a ruler and protractor work just fine. There is a danger you have with your more modern calculators when working with Pythagorean theorem and negative values. Please notice I have negative 2 squared, which should come out to be 4. Keep in mind that a lot of times when in your calculators, if you go negative 2 squared, the calculator processes that as negative 1 times 2 squared, so it will actually give you negative 4, which is incorrect. That's a processing error that they have always had in these calculators. You have to put everything in parentheses if you're dealing with Pythagorean theorem and negative signs. An easy fix actually is to kind of just work with absolute values, and you'll be fine with that for your triangle. Same thing when dealing with the angle. If you notice, I do not have a negative at all on the 2, and that's because if I put a negative on here, I'm going to come up with a negative angle. And calculators do not recognize 4 quadrants. As far as a calculator is concerned, there are only 2 quadrants. You see, if this 2 is negative, I'd come up with a negative 1.5. But let's say I had positive 2 and negative 3. I would also come up with the exact same value. So the calculator cannot tell the difference between my second quadrant and my fourth quadrant. Likewise, if both of these were positive, I come up with positive 1.5. If both of these were negative, I come up with positive 1.5. The calculator cannot tell the difference between the first and third quadrant. So you can never trust your calculator to give you an accurate angle or a correctly referenced angle just based on the numbers that you're typing into the calculator. This again is why it's so important to draw out your triangle. Then you can just put in positive values for your legs, find what the angle is, and then simply identify what your angle reference is going to be. So for example, 3 is my opposite, 2 is my adjacent. So this here is my angle. So this angle is going to be 56.31 degrees to the right of the negative y-axis. If I did not have this diagram, I would not be able to see that very easily. To find my displacement, as I said earlier, I can take my displacement vectors and simply add them up vectorially. Or if I chose to, since I have my velocity resultant vector, I can multiply that by the time and find my displacement that way as well. The options are up to you. There is no method that's more correct than the other. It just comes down to what approach makes you happiest. All right, that's going to wrap us up here. Hopefully this is making some sense. If you're looking at this video and you're going, I think I have this, you're in an excellent place and you'll have a very easy time in class. If you're looking at this saying, I think I'm starting to see some of it, but I could really use some help, that's exactly where you should be. And if you're looking at this going, I'm just not really getting a grasp of this, that's totally okay. The point of the video is just to give you an introduction so that you know, so that you can see what you need to know and you can see what you already understand and see what you need to ask questions about in class. Because as always, these videos are not about me getting out of work. It is to only prepare you for what we're doing in class. All right, so I will see you guys in class and have fun and stay safe.